Here's our second question on pulleys, and the last one in this little section of videos on forces and motion. So two particles A and B have these masses and they're connected by a light inextensible string. A lies on a rough horizontal table, blah blah blah. So let's get our diagram drawn for this. So we're going to draw a rough horizontal table. So A is lying on this 4.5 meters from a small smooth pulley, which is fixed at the edge of the table. So we've got a pulley at the edge of the table, like this, and we've got A here. We'll draw A as a box. So we've got a little bit more room. So this is A. It's 0.4 kilograms. So it looks like this. 4.5 meters away from a smooth pulley. So or A. This is 4.5 meters. The string passes over the pulley and B hangs freely, so we've got a string from A going over the pulley, and then B hangs freely, so the string passes over. Let's draw the edge of our table first. Edge of our table, and then we've got the string carries on. B hangs freely with the string taut, 0.5 above the horizontal ground. So then we've got horizontal ground here, and B is here. In fact, we'll draw B as a box as well to give ourselves room. So B is going to be here somewhere. So let's just check we've got everything we need. Two particles A and B, so A is 0.4, B is 0.8 kilograms. Put that in there. They're connected by a light inextensible string. A is on the rough horizontal table, 4.5 meters from a pulley, fixed at the edge of the table. A string passes over it and B hangs freely with a string taut, 0.5 meters above the ground. So we know that this distance here is 0.5 meters as well. Frictional force of 0.08 G opposes A. So if you think about when this is released, B is going to be going this way, so A is going to start moving this way. So that frictional force opposing the motion of A is going to be this direction, acting on A, and that's 0.08 G. Then we're going to have our reaction force here, and 0.4 G. We're going to have 0.8 G acting downwards here, because this will be accelerating downwards. A is going to be accelerating this way. And that's it. The system is released from rest. Find the acceleration of the system, the time taken for B to reach the ground, the total distance travelled by A before it comes to rest. Okay, so let's have a little look at each of these particles. They're connected, but they're acting, one's going horizontally, one's going vertically, so we can't treat it as one. So we're going to treat it as two parts of this kind of system. We're going to look at A and we're going to look at B respectively. So let's have a little look at A. So for A only, so for A we've got its motion is going towards the right, so our resultant force to the right, because when this is released B is going to drop down this way, and then that means A is going to go that way. So the resultant force will be to the right. And we know to the right, we're also going to have tension in the string, which I've not put in yet, sorry. So the string, so tension is going to be pulling it this way. So we're going to have tension going either way, this way, and then tension going down and up against this. If you think about the tension, is going to be pulling on the pulley this way and this way. That's where the weights are. But the tension in the string will go this way and this way here. So for A we have the resultant force, the force is acting to the right, is just T here. And then we've got the force to the left is 0.08 g, the frictional force. No other force is acting horizontally on it, and that's going to be the mass, 0.4 times the acceleration. So we've got two unknowns here. We've got t and we've got a, so hopefully we can form another equation with t and a in, and then we can solve simultaneously. And for b, the resultant force is going to be down, because when this is let go, db is going to head this way. And the downward force on b is 0.8 g. It's here. No other downward forces, and the upward force acting on b is the tension in the string t. So minus t, and that will produce the mass times the acceleration, the resultant force. And we've got two equations in a and t, so we can solve these simultaneously. So if we line the t's up, we can do equation 1 plus equation 2. So we get 0.72 g when we add these together is 1.2a, divide by 1.2, and we get a is equal to 0.6 g, 0.6 times 9.f if we want to work it out, and that's 5.88 meters per second squared. So the system is going to accelerate at the same pace, and that will be the acceleration of both particles A and B. Let's have a look at part B. The time taken for B to reach the ground. Well, with this we can find forces now. We can find the tension by subbing A back in. But if we're looking at the time it takes for B to reach the ground, then we know that it's going to be 0.5 meters to reach the ground. We've now got the acceleration of the whole system. So we've got S, we've got A. It was initially starting at rest, so we've got U. So for the time taken for B to reach the ground, the time taken for B to reach the ground, we've got its initial velocity is 0, the acceleration is 5.88, the distance it's got to travel is 0.5 meters, so we can work out the time that that's going to take using S equals ut plus a half at squared. So there's S, u is 0, a half, and we're just working the downwards direction here, t squared. Half of 5.88 is 2.94, divide that. .170. No, sorry, 170. Square root that. We will get positive and negative, but we're not doing with negative time here. So we get 0.412. 0.4123. So the time it will take to hit the ground, 0.412 seconds to 3SF. That's part B. Time taken for B to reach the ground. And then the total distance travelled by A before it comes to rest. So if we think about A is going to be accelerating this way towards the pulley with acceleration 5.88, the same as the whole system, which is written here. But what's going to happen is it's going to start accelerating, B is going to accelerate, but when B hits the ground, then the forces acting on A are going to change. So we need to think about what's going to happen to A when B hits the ground as well. So we need to split this bit into two bits of motion. The motion for A before B hits the ground, so in these 0.412 seconds, and then we've got to think about what's going to happen after A hits the ground as well. So let's split this into a couple of bits. So the first thing we're going to look at is we're going to find, if we find the speed of B when it hits the ground, that will give us the speed of A. So if you think about the first part of A, it will travel the same as B, same acceleration, etc., etc. It's going to travel the same distance as B before it hits the ground, because the whole system is accelerating in the same way. Both B and A are starting at rest. They're both accelerating at the same rate. So in that time here, A is also going to go 0.5 meters. It's all accelerating in the same way. Then when B hits the ground, it's going to change. So that's the bit that's tricky. So if we want to find out how far A goes, so A is going to go 0.5 meters. and it's going to get to here, and then it's going to hit the ground. We want to find this next distance, so we're going to need to find out some velocities, or well, we know that when A comes to rest, its final velocity will be 0. We want to find S, so if we can find its initial velocity, and we've obviously got acceleration and things like that, we can find our distance. So if you think about this, we're going to think about the second period of motion of A. We need to find its velocity when B hits the floor. So it's going to go 0.5 meters that way. B is going to hit the floor. So if we can find out the speed at which A is traveling, we know that A eventually will be 0 speed, as I just said. So it'll finish at 0 meters per second. If we can find its initial velocity, U, we know that should be the same as the speed at which B hits the floor, because they're both starting from rest. They've both got the same acceleration. They're both traveling 0.5 meters, etc., etc. So if we find the speed at which B hits the floor, we'll also have the speed at which A hits the floor as well. So let's find the speed at which not A hits the floor, sorry, the speed that A starts to then decelerate. So for B, we've got its initial speed was 0. We're trying to find its final speed. We've got that it's traveling 0.5, and we've got the acceleration is 5.88. So there's probably various ways of working this bit out. So v squared 0 plus 2as. So v squared is 5.88. And the square root of that is 2.42. Etc., etc. So that's the speed that B is on the table. So this is when B hits the floor. That's the speed which A is traveling after its initial 0.5 meters, because remember we're trying to find the distance that A travels, aren't we? So it travels 0.5 meters, and after 0.5 meters it'll be at that speed, and then it's going to start decelerating. So let's think about how it's going to decelerate. So when B hits the ground, the string goes slack, and A will start to decelerate. So if we go back to where A is on the table, then we know it's got its weight, that these two forces acting this way. This force is now taken out of the equation because the string has gone slack because B's hit the floor. So we can take that force out, but we've still got that resistive force of 0.08. It was 0.08, wasn't it? 0.08 G. So we've got that acting backwards against it. So our resultant force for A, we're still going in this direction. So we're going to have no force acting towards the right. But we've got that force acting towards the left, so therefore minus 0.08 G. And that's going to be the mass of A, which is 0.4, times its acceleration. This is now its acceleration after B's hit the floor. So it's accelerating for the first 0.5 meters, and then when B hits the floor, it's going to accelerate differently because it's not got those same forces acting on it. So A will be minus 0.08 G divided by 0.4 minus 1.96. Okay, it's minus because it's actually decelerating. So now we've got the acceleration. We know we're waiting for A to stop, so its final velocity will be 0. Its initial velocity is here. And we can therefore find the distance that it travels in this second part of motion. So if we use v squared is u squared plus 2as. V is 0. U is that 2.7. Or 2.42, sorry, so square that, you get 5.88. But let's do it in bits. Plus 2a s. And we should get S as 1.5 meters. And therefore A travels the original 0.5 plus the 1.5, which is 2 meters.